Welcome, ladies and gentlemen, to our panel discussion featuring the Breeze Scientific Advisory Board, a group designed to provide strategic advice to Breeze's technology development. The lithium-ion battery, the heartbeat of our modern world, powers everything from mobile devices to electric vehicles. The pursuit of enhancing the safety, performance, and sustainability of lithium-ion battery is not only a scientific endeavor, but also a global imperative. We have the panel here today representing the vanguard of this quest. So our first member here, Professor Gregory Plett, is a pioneer in the field of battery management system. His research paved the foundations in battery control, and his influential textbooks serve as essential resources for researchers and leaders in this field, which is everyone's starting point to learn about battery management systems.
Well, thank you for that kind introduction. Yes, my name is Gregory Plett, and I'm with the University of Colorado at Colorado Springs, and it's a great pleasure to be here today.
So our second panel member here, Professor Matthieu Dubarry, is an innovator in using new techniques such as incremental capacity analysis in the field of battery prognosis, and he has developed numerous software tools in this field. His research has truly advanced our understanding and quantification in battery degradation, not only at single cell level, but also at pack levels.
Thank you very much for the kind introduction. I'm Matthieu Dubarry from the University of Dubarry at Manoa, and I'm really happy to be here today.
So our third panel member, Professor Gregory Offer, is renowned for his exceptional contribution in understanding and modeling the behaviors of battery systems. He is today the principal investigator for Faraday Institution's multi-scale modeling program, one of the largest battery modeling research consortia in the world.
Thank you, Jingyi. So I'm Greg from Imperial College London, and it's a real pleasure to be here.
Last but not least, our fourth panel member representing Breeze is Dr. Zhao. With a strong foundations in lithium-ion battery design, thermal management, and simulation, as CTO, he is the driving force behind Breeze's physics-based battery management software.
Thank you, Jingyi. I'm Yan. I'm CTO and co-founder at Breeze. So I will introduce Breeze a little bit. So Breeze, we founded Breeze back in 2019, spun out from Imperial College London, where I met my co-founder, Greg Offer, and also Ian Campbell. Today at Breeze, we develop physics-based battery management system for some of the world's most iconic automotive and consumer electronics brands. And we are very excited to be with our scientific advisory panel here today.
So we are kicking off with a bang. The first question to the panel is, what are the recent breakthroughs in lithium-ion battery development that got you excited the most? And how might they transform our lives? Let's go from Greg.
I think there's a lot of interesting things that are happening in the lithium-ion battery design field right now. There's different chemistries that are being introduced, and they bring their own advantages and disadvantages. So some of them are bringing more energy density, which means that a vehicle, for example, could travel a greater distance with the same size of battery pack. And some of them are removing toxic elements so that they enhance the sustainability. So all of these bring different challenges to the battery management field, and I think that it's a very exciting thing to be in right now. There are some prospects on the horizon which are maybe not quite here yet, and I find those even more interesting. So replacing perhaps lithium-ion with lithium metal batteries, or even with lithium sulfur batteries. And these are things that are going to be possibly very exciting in the future, and so far I don't know what the answer is.
So you briefly touched about the concept of energy density. What do you think that means to the end user?
So energy density is either how much energy I can put in a specific weight or a specific volume, depending on exactly how you define the term. So if I have an electric vehicle, I want to have, if I have more energy density, that means I can drive farther. And if I have a phone with more energy density, that means that I can use a smaller package to have the same amount of conversation, or with a slightly larger package, I can use the phone for a longer period of time. So all of these, I think, are very appealing to the customer.
I would like to throw the same question to another member of the board, Matthieu. I wonder what's the one thing that got you most excited about?
I think recently we've seen a big push towards data-driven methods, and so that's kind of opened new horizons for what we can do with batteries and open the key question of data. What's good data? Do we have enough data? Or can we generate new data that's useful to the community and try to develop better algorithm for battery management system and be able to adjust more easily to those new emerging chemistries?
I wonder, Yan, what's your opinions on how we could leverage on the burst of data and the burst of machine learning strategies?
Yeah, I think it is obviously a super exciting topic in grand scheme of, I guess, generative AI or a general excitement around AI technologies. I would say for batteries, we don't yet know. Maybe that's a good reason to explore more. But I think I'm sure in any other field that we find in the last 20 years, there's always something we can get out of data eventually. So yeah, I'm super excited. Maybe I don't know yet what that exact thing we're looking for yet.
Greg, from the modeling perspective, do you see any synergy between physics model and the database-driven approach in the next 5 or 10 years horizon?
I think there's already synergies between the two. I mean, the models that we can create now that are on a pathway towards predicting lifetime. We're not all the way there yet, but they're already beginning to be useful, and we can already run them so fast that we can generate data faster than we can actually analyze. So we already need machine learning methods in order to just analyze all the virtual data that we're generating, which can augment the experimental data that we gather in the lab.
So I wonder if now we've explored the lithium-ion battery development and we sort of naturally drift into the field of data, and what does it mean for our control strategy? Can we make our control strategy better based on the data we have and derive what's meaningful from the data better?
I think there's so much we can do with the data we're currently generating, whether that's in research and development, but also transmitting back from devices and vehicles that's being deployed. But as a company, we still feel the pathway with the physics-based battery management system, there's so much we can do there. And I think as our panel have been discussing that, I think where we have physics, we should rely on physics. Maybe where we have exhausted our way of using physics, and that's where we should look towards data.
And I would like to add that it's really important to have a varied data set when you want to train a machine learning algorithm. You don't know how the set is going to be used in the field. So being able to have a lot of data is great, but generating data, whether it's a physics-based model or more other type of model, is extremely important to make sure the algorithms going to be effective under any possible condition the car or the grid storage system going to experience in the field.
So Matthieu, just to add on to that, do you think the data quality improvement can be a big step up for battery control based on physics model?
Oh yes, absolutely. And I think there's a lot of different modeling options we can consider, physics-based or not, to generate synthetic data that's extremely clean, and that can be representative of all the possible degradation the battery could see in the field. So to a point with those type of models that we don't really need the experiment to know what the cell is going to be like once degraded. So we can use those models to generate a vast array of data, really varied data that we can use to train and test a lot of different algorithms and get some set of certainty on how applicable they're going to be once they're deployed in the field.
So I wonder to get some other additional opinions from Greg. We know that the online updates of parameters is almost ready to be deployed. And how does that influence the accuracy of the model, and how does that improve the model's control to extend the battery's lifetime and performance?
So I think advances in models have come a long way in the last few years, and yeah, certainly in the academic literature, what you're referring to appears like it's going to be possible in the very near future. And I think that will enable these algorithms to be more reliable, more accurate. Ultimately, it's going to have an impact on the user experience. So if you're better at state estimation and those states have a meaningful impact on the way the customer is using the device, then they're going to be, they're going to be worth something. So an example at the end of, close to the end of discharge, if you're in an electric vehicle, you really want your range prediction to be accurate. The consequence of getting that wrong for the customer could be breaking down on the side of the road. So of course that's really attractive. So getting that right is very important.
Maybe I think it would be super interesting to hear, Gregory, your perspective on what are the challenges of, I guess, as these models getting more complex and updating these parameters online.
It is a very complicated thing to do well. And I agree that it's one that we need to solve, because if we use a single model to describe the battery through its entire life, it may work very well at the beginning of life, but as the battery ages, that model will not continue to describe its behaviors very well. And we may end up with the scenario that Greg mentioned of someone being broken down on the side of the road because the model failed. So somehow we have to have a model that describes the battery cell well at its present state of life. There are a couple of methods to do that. One is if we can somehow use the data that we're continuously measuring to adjust the parameters of the model, that could provide a very satisfactory answer. Another is if we have a bank of battery models that are representative or descriptive of a battery at different stages of life, and we simply select which model to use, that is another alternative. And at this point, I don't know what the right answer is between those.
Maybe a question for both Matthieu and Gregory is that, do you see any opportunity to intervene a controlled scenario where making these online parameter updates easier from I guess, how we operate the vehicles?
I mean, it really depends what accuracy and what you want to look for. You can look at the degradation mechanisms, and then it's really complicated because there are a lot of them that require a lot of parameters. Or you can try to get like one level above that and look at degradation modes, the loss of lithium inventory, the loss of active material, that are a little bit easier to determine online just from the voltage response of the cell. So to me, those kind of models are really useful for really quick diagnosis of the cell online, because it's just use the voltage and it's pretty easy to determine.
Yeah, just to add on to that, some of the physical models of degradation are quite complicated and have many parameter values, but in actuality, only a few of the parameters are dominant in the response, so we may be able to get by with estimating only a few.
I would like to ask everyone in the panel that we now have so many powerful and elegant advanced models out there, but they're not being widely used to power every single batteries in the devices. What do you think is hindering us from doing that?
So I think the OEMs are doing a really good job with what they have, and one of their jobs requires them to naturally be a little bit conservative. They have to make sure that devices meet safety requirements. There are certain capabilities that need to be guaranteed for the customer. So we can come along and we can offer them new solutions, but it's the right thing to do to wait for validation of those benefits. So there's a natural conservativeness baked into the industry for the right reasons. But that said, things do move on, and these advances can offer significant improvements. So I think one of the areas where we see the most opportunity is over-the-air updates. So where manufacturers have embraced the ability to change the software in existing products, once it's been proven to show benefits, then you can roll out those benefits to millions of consumers all over the world.
And I would add to that many of the academic work is done at the single cell level. And when we're talking about grid deployed system or electric vehicles, we're talking about thousands of cells in a battery pack, which add a lot of complexity in the modeling. So it takes much longer to validate all the great models. Greg mentioned to be conservative, it takes a lot of time to deploy that at the battery pack level, which have a lot of inhomogeneities, a lot of balancing, a lot of other parameters to consider, temperature gradients and others, to be able to take that into consideration to get a model that works pretty well for deployed systems.
And as Greg also mentioned, the nature of the business tends to be very conservative, and so why do I want to change something that already seems to work? So yes, what we have now works, but we believe that the physics models are going to unlock higher levels of performance, so perhaps more performance for the same life, or perhaps longer life for the same performance than some of the conservative models that we're using today. So I feel that there are really big benefits that are coming out of this.
Throwing back to Yan, I wonder what's your opinion on, is the wait time worth it? How should OEMs strike a balance between making sure the quality is there and also not losing out on the opportunity to differentiate themselves?
So zooming in into battery technology and the models specifically, where I do believe the models exist today and still have some way to go in terms of balancing between number of internal estimates the model can generate to the parameterization effort and down to the implementation side with computational speed. So I think there's still quite a long way that we need to go with a physics-based battery management system to kind of satisfy these optimizations to make sure they can actually implement it into a battery management system that ships out to the customers.
So moving on to the next topic, we know there are many metrics that will guide us into choosing and gauging the battery performance. For example, the kilowatt hour per liter for energy density and some other cost considerations like cost per cycle. Where do you see the bridging between those two different perspectives from purely the cost consideration and the performance consideration from the materials perspective? How can the OEM combine these two perspectives and help them to place the best bet in the battery management systems?
The most sophisticated OEMs that we talk to, they take a more nuanced view to the metrics that matter to them. So the energy density that you get on the spec sheet of a cell isn't actually what the customer experiences. You know, it might be charging time, you know, the amount of energy that you can get into your product in a fixed period of time, 20 minutes, 30 minutes, 40 minutes. So it's that usable energy density that matters more to the customer. So where an OEM understands this and they have good differentiation in the market space, you know, in terms of what they know matters, then we can work with them to help achieve this. Other traps to avoid is focusing on any one measure on its own can often lead an industry into a subsystem optimization trap, which we see quite often. So just targeting cost or energy density can often then come at the expense of a cell that's very difficult to thermally manage. And then this leads to large inhomogeneities within the cell, which makes state estimation much harder.
And I would add to that it's also important to realize that there are many different chemistries on the market and that depending on the application, some chemistry that make much more sense than others. For example, if you want a battery that's going to stay fully charged, it's probably better to look at battery with lithium titanium oxide rather than graphite because we know there's going to be far less calendar aging. So looking at both the modeling aspect to look at what chemistry is most adapted to what application, I think it's a really important topic, both for OEMs, also for the customer to be informed on what chemistries are available and not be focused on a single chemistry and a single manufacturer, to look around and look for other opportunities based on the specifications they need.
I mean, from I think my perspective, that I think any performance matrix that is any manufacturer that optimizes has to be baselined on a per dollar basis. Is how many dollars I'm getting my charge speed increase, how many dollars we're getting extra life. I guess this is where I think Breeze as a company, we're trying to pursue a different path via battery software that would enable OEMs to achieve these advancements in performance or different trade-offs or utilizing the existing materials better via by far a more cost-effective method and a faster method.
So we briefly touched on the different chemistries in materials. I wonder, as we see the many promising and emerging candidates like silicon, sodium, solid-state battery, will this pose a challenge to battery management system, or there will be new opportunities in the control strategy?
So whenever we've received a new battery in our lab of a different chemistry from what we've seen before, there have always been some different features in it. And so yes, there are unique challenges that we need to solve every time a new chemistry comes along. So there may be hysteresis in the model, for example, or it may be that they age in different ways. And so we see this as opportunities that software can help to solve in battery management.
Maybe I'll add is from a material perspective, and every new generation of new material comes in, inevitably it is better in some way, but it also comes with challenges. But for battery software, that's exciting because that's where we can show maximum amount of value by making up those, I guess, short to medium term deficiencies via a better control or software strategy. So I think we do see it as an opportunity rather than a hindrance to kind of advancing battery as a product.
Yeah, I'd also say that by taking a physics-based approach, then you can deal with those differences when they emerge, hopefully more quickly. You know, if the physics is similar enough that your models already include it, and you just need to adapt in a certain way, then you can respond much quicker than having to go all the way back to the beginning and start with testing. Obviously, with some of the really new battery chemistries coming along that might be fundamentally different, then it may take a little bit longer.
But ultimately, every battery management system set of algorithms needs to produce the same kind of answer. You need to have a state of charge, something representative of the health of the battery and the power that's available and so forth. So from a software perspective, your customer will have the same needs, and then you can learn how to create the software to fulfill those needs.
Yeah, so if the methodology is mature, then you can go through it more quickly the second and the third and the fourth time.
Yeah, I'm wondering, Matthieu, does this put additional stress or does it create more opportunity from a diagnostic?
It's always fun to try to see something new and find the new way in. I mean, it's every new chemistry is a new puzzle, and we can use past knowledge, but it's each time we're going to discover something new and find a new key point, a new thing to look at. So for me, it's really exciting.
So we have so many fantastic options in front of the OEMs in control strategy. If you put yourself in the OEM's shoes, in particular the consumer electronics and car manufacturers brand, what's your best bet for the strategy to differentiate in the next 5 to 10 years?
So I think in the consumer device space, one of the biggest questions is how long can I operate my device before I run out of charge, before it turns off. And if we can differentiate by even predicting that a little bit more accurately, that is going to be very valuable for the consumer. And I guess there's a very similar problem in the automotive space. If I can predict when my vehicle is going to run out of range, that's going to be a big improvement.
And adding to that, I think adding sustainability and adding the battery that are easier to recycle or adding battery that are easier to use for another application, I think. So if we can get batteries out of the first use and know their state, know the state of health, know the degradation, try to forecast what's going to happen next, it's going to be really useful for the second use, and that might give those users a big lead in helping reduce the number of cells we need to recycle right away and make sure we use the resources we have to the fullest.
I think for me it's about price. So to really, when we founded Breathe, it was called Breathe because we care about air quality, and so rolling out electrification for the vast majority of the world's population has to be the end goal. Where those batteries come from, sustainability is extremely important, and where they go at the end of life. When you buy a vehicle, for the majority of the world, it's going to be about price. It's going to be about cost. And I think software is a key differentiator. As Jan said earlier, it's about how you can get the most out of the materials that you've put in that vehicle in the first place. And that helps drive the costs down so that more people can drive electric.
So from a Breeze's point of view, the two markets is very different. For consumer electronics, everything we see has to be based on a continuously improving runtime on devices. On top of that, we have to offer consumer more convenience in form of faster charging, but also a more sustainable product. It means the number of years that battery would have to last. I think these three things are competing, and I think that's where we see our software play the biggest role in this particular market. And in automotive, I very much echo what Greg says, and every bit of this, both in cycle life, range, safety, as well as the sustainability, has to be based on the foundation of this has to be on a per dollar cost competitive platform. So I think subtly different, but I still think every manufacturer needs to seek competitive edge everywhere, and obviously we're working hard to provide that via battery management software.
One last question. We're going to end on this very important topic. So the world isn't decarbonizing at the rate required to meet its target. I believe we are here today in this room, in this industry, because we believe batteries can be a solution. What do you think is us as scientists, engineers, and leaders in this field can do one more thing that can help increase sustainability?
That's a very good question, and my perspective on the battery management algorithms is that the battery manufacturer and supplier has already done their best job of creating the best battery cell that they know how to make today. And my job then is to understand how to use that battery cell so that we get the most performance and the most life out of it. And I think that will be a contribution towards sustainability because we're not wasting the resources that we have.
Yeah, really important question. I fully agree with what Gregory just mentioned. I think also trying to develop the software to allow to use the battery better, whether it's optimizing the charge or allowing the charge to do something else. For example, for electric vehicles, we could imagine doing vehicle to grid where the batteries could help the overall grid. So that would reduce the need for additional storage on the grid. So trying to develop software that can do that efficiently without inducing any more degradation of the batteries, to me it's really interesting and can really help, especially island nation like for me in Hawaii, where the land is quite limited. So using the EVs that are parked 90% of the time as grid storage would drastically help reduce our carbon emission at the island level.
So for me, it comes down to cost again. The more we can drive down the cost to the consumers, then the faster the electrification transition will go. And actually in a way that the detractors won't be able to criticise as strongly, because if the product is better than the incumbent, then the transition will just happen and it will be exponential.
I think there's only one solution, and I very much agree with what Greg said. It is about building more compelling products. And from a Breeze point of view, I think we have to help our customers, ultimately end users, to give them a more compelling product. And from a battery perspective, I think that's the way where we can help to accelerate the transition into, I guess, a more climate positive future.
So thank you everyone for joining us today and to have these very insightful discussions. We hope the discussion today continue to spark meaningful conversations between the OEMs and other stakeholders in this industry, bringing us one step closer to sustainability.